is the room for the SCHC working group. If you're looking for something else, you're probably at the wrong place. Okay, so let it start. So welcome to the IETF 120 and to pretty much the first session for this IETF. So welcome all, and I hope you will have a very fruitful week. This is an official IETF meeting, so all note well that some of you are used to apply to this meeting, in particular the rules for IPR. So if you're aware of any IPR that is not disclosed on any subject that's being discussed today, please let us know or refrain from discussing at all on those ideas. The code of conduct also applies. I'm sure you will hear a lot of about it. So please read this slide. It's available in the meeting papers. And there is the meeting tips that you will see also on every discussion this week. So this is the first time, so we can go through it. There is an application for your phone and a special login in Mitico if you're attending within the room. So please use that tool. You will use it in particular to ask for the mic and get in queues. So please go to the agenda if you're not aware of it. And on the SCHC line, you will find that there is this button that you can press to get to the on-site tool. And all the usual resources that you will see every day this week. So we have the usual agenda bashing, and at the end, we'll have a small discussion on the OAM draft. So Laurent, I will ask you to go to the mic a little bit before the architecture time, just to let us know what you think will happen on the OAM draft. I know that you have tried to publish and something happened, so you will tell us what the future is for this draft. So after the agenda bashing, we'll discuss the agenda, the SCHC architecture, and Laurent, that will be you as well. So we have prepared a number of slides and a good number of slides that we'll be presenting. Please try to stay within the 40 minutes, 45 max, because there is a full agenda after you. So there are a lot of interesting topics we want to discuss in this architecture, but please, let's try to end before 10:30. Then Carles will present the progress and the discussion we have on the SCHC over 15.4. After that, we'll have Marco on the 8824 update. Then there is this new work which used to be called Zero Energy Devices, and Anna will present it from remote. That's Edgar and Anna working on connections that can be disrupted and how SCHC can be used to transmit data, either because we lose the connection at all, or the time to transmit is very, very long, so we can't even think of it as a connection. Then we'll have Javier. Javier will present the open source SCHC implementation. It's a very complete SCHC implementation coming from Aclio, which is now open source. So that's a very interesting move for our group. So Javier will present all that. And at the end, we'll have Mariam and Sandra, I'm not sure whom, because I was not really told that, who will present two drafts which come from IPsec.me, which are leveraging SCHC for IKE and compressed security encryption. And if there is any time left, we'll have an IOB. Quick status on the draft. You see that the OAM draft at the very end is still close to expire, but that's not the goal. I mean, Laurent is updating it, so he will present that to us. Apart from that, well, Marco just published an update of 8824, so he would present that. We hope we can move on with the SCHC protocol number. Bob is here, so that's good. Eric has made a review of the draft, and there are 2 sections that we need to fill. I mean, it's just to get them like, why are we doing this in the first place? So Bob, I'm happy to work with you on that just to complete those. But we have asked a early review from IOTDIR in DIR to see if there are some topics which are missing for a document of this type. It's a very short document, just asking for a protocol type and an ether type. Then the SCHC architecture will have 40 minutes to discuss it, where we are, where we want to go. So basically, it's more complex than we thought, because we started SCHC on a point-to-point, a very specific type of connection, like LoRa or Sigfox. And now we're extending that to SCHC over the internet. And there are a number of questions about how you set up the context, and even there is the question of, is it really point-to-point, or do we have point-to-multipoint? There are a number of questions like this, which the architecture needs to address, which were not represented in 8724, 8824. So that's for the workgroup documents. Access control
Pascal,
is expired, I guess. Yes?
Yes, just one point on the SCHC over zero energy devices, which is now, of course, with the new name that will be presented by Anna. So we had the working group at the call for adoption, that ran for 2 weeks before, and then with the change with the introduced name. Yes, and so we timed it so that the call for adoption ends now, like before this meeting, and we only +1s. So on this one, I think we're good to, we have adopted.
Yes, we will be announcing adoption during the presentation for this document. So SCHC over PPP, I guess, is stalled as well, because it's done for its purpose, but I guess it will be revised once we have the architecture straight, so we can position the work within the architecture. And maybe we will have to move things around and do things a bit differently just to fit better in the architecture. It was maybe the first example where we did some SCHC over the internet. So it opened some prime. SCHC over 15.4 also opened some primes to the original designs. And once we have those things straight in the architecture, then we can, I guess, progress on the SCHC over PPP and complete it. FEC, we don't have a presentation on FEC today, so that's basically an idea that came up after the discussions with Bob. So using FEC, so forward error correction as opposed to reactive error correction in the SCHC fragmentation recovery. And that's pretty much it. So Laurent, I will give you the mic.
Okay, so for OAM, we issue 2 weeks ago, but it failed, so I issue it this morning. So it's a little bit late, but it's version 4 of the draft. So we review almost all the document to make it clearer, to have better explanation for the compression rule. And the main part is that we remove the action part, which make no consensus on the mailing list. And so now we have, I think, a more consensual document that is doing ICMPv6 compression, and introduce also 2 new CDA and 2 new matching operator to compress existing rules. So I don't know, what do we do now if we have to start a new working group adoption?
Well, I mean, it was, we never actually closed the adoption call. We had the adoption call going, and we had all these, as you said, discussions on the mailing list, and we had this gray area. And thank you for actually going forward and removing the gray items that we had these ongoing discussions. So I think that, I mean, it is now, you submitted a new version. Then the proper thing to do is, to continue the adoption call for 2 more weeks, and then and then we end the call, and it can become a working group item, right? And especially the people that were like against the actions being there, you know, if they can say on the mailing list, hey, it works for me now, like +1, then we know that it's all solved, and you can submit like after the IETF, like 2 weeks from now.
Yes, I believe people didn't have a chance to look at the new document, so it's a bit useless to make a show of hands right now. Let's do it on the mailing list. If Lorenzo is listening, Lorenzo, there is effectively a huge difference in setting of volume between the people remote and the room. I mean, I could barely hear Laurent on the mic, so I had to push the volume on my PC. And when Alex talked, it was like an explosion in my room. So yeah, please see if you can tune the volumes differently for in room and outside of the room. Lorenzo, if you hear us.
Okay.
Any question for Laurent? I'm hearing none. So Laurent, please stay there, and we'll move to the architecture discussion.
And thank you, Laurent, and for the other authors of, you know, finding the way to move with the OAM draft. So that's really nice. Thank you.
Okay, so I will talk now about the architecture. So it's not only my work, it's a global work that has been done. A lot of discussion between Anna, Alex, Pascal, and me about the technology. So here I have some echoes. Mic is open.
It's missing.
So the idea is to review the architecture, because it's a long document that has been published a long time ago. And the goal, if you can go to the next slide, Pascal. So it's comes from the origin of SCHC, because at the origin it was developed by the LP1 working group. And so SCHC focused on an architecture that was generic and correspond to different LP1 technologies. But now we have to extend this. So we have the RFC 8724 that gives the first architecture, then 8824 that introduce also a different level of SCHC that is not very precisely defined. And we have also a young data model for the rule. And we have also to put this young data model into the architecture. So the goal of this document first is to remove the dependency to LP1 and have something that is understandable with only SCHC. We are also to focus on new topologies. So LP1 was almost a star topology, and now we have a 6 law, we have IPsec, where we have a mesh network under SCHC. So we have to see how to handle it. And as I said before, we have boundaries that appears that force us to have different level of SCHC. So we have what we discover in 8824. It's the cryptographical boundaries. It means that you have something that is in plain text and things that is encrypted. So you have to do the compression before the encryption. We have also some element in the architecture that has to be placed at some location. So we have these different things to take into account, and of course to integrate the management and all that stuff in the architecture. So next slide, please. So on the next slide, we will have missing something. Okay, we have the old architecture that was from 8724, where we have this strong dependency to LP1 by the name. We have the device, we have the application, we have the network gateway, and we have something that was not named in the architecture, but implement the SCHC fragmentation reassembly and the SCHC compression decompression. So now we are moving to something that is more agnostic to LP1. So the first thing is to introduce an element that was not named with LP1. It's what we call the SCHC network gateway, or SNG, which is at the boundary between a SCHC network and a non-SCHC network. So here we don't say IP because SCHC can also appear, for example, at layer 2 with, I don't know, for example, Wi-Fi allo that wants to do compression, and we have the regular network. So here we have something that is generic and is not focused on layer 2 or layer 3. So from this SCHC network gateway, we can give a definition to a device, and we keep the name device because in the rule we have this name that appears. So we have to continue to use it in the architecture. And so the device is the element that do SCHC with the SCHC network gateway. And at the other end of the network, we have the application, and it's where and the application is the entity, the device talk with the application. So when you send packet, you have the compressed part and the uncompressed part. So what we can define also is a SCHC instance. So the SCHC instance is two endpoints that are implemented SCHC and share exactly the same set of rules. So here we have this set of rules that is exactly shared. So then we can stack things and keep going on this definition. So on the blue part, we have an instance that go to the SDN, but we can have also another endpoint that go directly to the application. So in that case, since we have name, can you go back, Pascal? Since we have named one part a device and the other part the application, so we continue to name them device and application. But there is cases, and that's the next slide, where we don't have this SCHC network gateway in the middle. So that's the case, for example, for 6LoW, where we are sending compressed packet over the network, and maybe we don't go outside to go back to a regular IP, or in IPsec also, where we are sending IP packets, and these IP packets are carrying SCHC messages. So in that case, we have to define what is a device, what is not a device, and here it's the implementer that will say which is one, and that's very important because this way we know what is uplink and downlink traffic. So now I will introduce something that is not so easy to understand, but make us the notation easier. It's the fact that when we put a protocol name into parentheses, it means that we are doing the compression of this protocol, and this is the result of the compression. So there is no details on the bits that are sent on the wire, but says that we are, in that case, compressed protocol P1, P2, and P3, and they are compressed by different instances of SCHC. So if we had only one instance, it will be parentheses P1, P2, P3, and other parentheses. Here, the fact that we have three set of parentheses means that we have three instances. And of course, it doesn't matter, it doesn't explain what you have on the wire. For example, if you have a rule, an instance where there is only one rule, then you don't need a rule ID because there is no prime. And if your compression residue is null, it means that you will have 0 bit on what you are sending. But in an abstract notation, you are sending this protocol very, very compressed. So it's what this notation is represent. So here we introduce those terminology. So we have maybe I will let you read, or I always explain all that. So we can go to the next slide. Or you want me to read it? So the new things we introduce in the architecture is we introduce a stratum because we didn't want to use layers because we think that layer is confusing. Because as I said at the beginning, when you do compression, for example, you can compress IPv6 and UDP using the same rule. So you have two layers, IP and UDP, that are compressed the same way. And when you go to CoAP or any encryption protocol, you have a plain text and you have something encrypted. So you need two SCHC instances to do this. And so if we stay using, if you continue to use the layer, maybe it's too confusing. So that's why we prefer to propose, or we propose stratum. So if you agree or not, you can say to us. Alex, I see you're in the queue.
Yes, thank you, Laurent. Would you like for us to pose like two questions now or at the end of the presentation?
I think you can interrupt me when you want.
Okay, yes. So yeah, I mean, one of the things is that yes. Of course, one of the things is that the architecture, like it needs to be something like readable and understandable by everyone. So I imagine that also anyone in the public can also in the room can ask questions, right? So I have a particular question that we discussed before, so I think this is the right time. So on the previous slide, when you talk about SCHC instance, you know, the way it's defined until now, it's like two SCHC endpoints. Like the SCHC endpoints are the pieces of software, let's say, that are doing the SCHC magic on the different devices, right? And so the SCHC instance is the thing that is, you know, covering these two endpoints, right? And one use case that came up actually very recently is the multicast, right? So we have in LoRaWAN and in DLMS in particular, we have a point-to-multipoint multicast, and it's like standardized in several places. So do you feel that we need to really focus on two SCHC endpoints, or should we frame it as like two or more, and then in the document say, well, of course, when you have more than two SCHC endpoints, there are other set of problems that are there. So probably we need to treat them differently. And I mean that's a question to you, and maybe you can also see the public, the people in the room as well, right? Yes.
So from my point of view, it's better to insist on the fact that we have a point-to-point association, because it's really the way SCHC is working. And so there is two answers to your question. The first one is that if we have multicast, in all the cases, the source address is not the same for all the nodes. So normally it means that you have different rules to manage the multicast, even if you have a multicast address as a destination. So this is first thing. Then maybe we can have some places where we will have the same set of rules for different elements, because they are you are not sending this or ignoring the same kind of information. But I think it's better to keep this point-to-point association, because this is really the fundamental of SCHC. So Pascal, I don't see all the cues. So Pascal?
Yes, I think the way I see it, we should, in the instance, allow for multiple endpoints, but describe first exactly as you say how the point-to-point works, and then have a specific sections on if you are doing point-to-multipoint, here is what happened. Is it just point-to-multipoint? Do you have multi-point-to-point? Do you have multi-point-to-point, rendezvous point, and then point-to-multipoint, which now is a multicast? And what does it mean? What does it mean in all those cases? The idea being to be able to retrofit multi-point-to-point and point-to-multipoint back into the view for each device of a point-to-point. I mean, if the device, for instance, if you do point-to-multipoint, there is one source and multiple receivers, but the destination is the multicast group. If you're just doing that, I mean, the devices, on the other hand, they see a point-to-point conversation. They don't really realize they are receiving firmware update over the air, for instance, that is distributed to more than one device. They don't see it. If we can say, hey, we define point-to-point very clearly, every detail, and after that we go and explain how that can be extended to point-to-multipoint. I mean, I don't think the architecture should bar it at this point. But
Last Bob Moskowitz. Last night in the hot RFC, there's a presentation on the multicast port problem, Stuart Cheshire, the thread work that he's doing. And I look at that, and that's a perfect application of SCHC in a multi-point environment. And so we have a specific use case that we can look at, and instead of the complexities of yet another set of solutions that hackathon effort is introducing, say, this can be handled through a SCHC crew, I think. So I think it'll be a good exercise for us to look at that work and say, could this be done with SCHC, and if so, presented as a counterpoint to that work? And there is thus your specific use case for multi-point to move forward on.
So yeah, I agree. So that's a good exercise to do. So for me, the two things that if we have multi-point, it doesn't mean that we have the same rule, because some variables are not the same for all the packets. The second thing is that we have also management, and management is a way to synchronize rules together. And in point-to-point, it's quite easy to maintain, because we have to be sure about the atomicity of both ends. If we are in a case where we have several nodes to synchronize, I think the protocol will be much more complex, and it's something we don't have any solution right now. So for me, it's better to start with point-to-points and maybe study how the impact of multi-points on it.
Laurent, I think I said something very similar to what you said. It's just that the difference is, let us, in my view, and I guess Alex as well, let us allow the instance to be between multi-point, or let's define something over the instance when it's point to multi-points, like a multi-instance or something. And then keep the document exactly like it is, the explanations exactly like they are, but then have a section for multicast, even if it says, hey, it's going to be another document. But something which says, hey, it will be part of it. In the end, we have to look at the number of programs. Maybe in this document, we just expose what those programs are, or maybe if they are not too big, we just work on them. But I'm like Bob and Alex, I don't think we should borrow it from our definitions.
Daniel?
Hi. So, yeah, so my understanding is that we really have the assumption that it's a communication between two endpoints, and that we understand exactly what is the data transited between those two endpoints. I think it's nice to keep it this way, and not to make it more complex, because one of the things we went to, even if we don't talk multicast, but if you don't say it's an endpoint where you assume you know what is being provided by one endpoint to the other one, is that if you think about traffic and you compress that traffic, but you end up in a SCHC packet, but there is an underlying assumption that the incoming packet is not already a SCHC packet, because if someone can send a SCHC packet, you have two states that are of the same name, and this is something we don't want. I mean, it can easily happen if we get out of this end-to-point communication. So I don't think we should start boiling the ocean about that. But I think it's really important to keep in mind that when we say it's end-to-point, it also means we really understand what the communication is about, and it's probably sufficiently complex with that.
Okay, thank you.
I mean, that's just my personal opinion.
Okay. So maybe just also for interest of time. So I think that there are there's obviously something into it. So probably maybe we need to add another name to that, or something like to say, okay, this is a point-to-point instance or something. But maybe we should move that to the mailing list. But I think it's really important, and also for this architectural document. And this is the type of discussion that I think is really important. And thank you very much, Laurent, for bringing all these points here. That we have this discussion, and with this awareness of Okay, like we are choosing really how to name things, and it's really important that we get these names correct, because like these are the concepts that finally structure the whole work. So yeah, and very, very interesting comments. Thank you.
Okay, so let me continue and introduce what we need, why we need, what we will call a stratum instance. So here is an example. So I don't say how IPsec compression will be used. That's we will have a presentation just after. It's just an architectural point of view. But say, for example, here you have a device that sends IPsec messages to an application. So here we see with the parenthesis notation that we have a first compression of the IP with the next stop that say is chick. And then you have the outer and inner IPsec header that are compressed, and then you have the data. So on the next slide, we go to the network. Pascal, if you can go to the next slide. So in that case, so we have uncompressed the first part. So now we have an IP packet, a real IP packet that say next stop is chic. And this way, when the packet arrives to the application, it can be managed by the chic machine to do the uncompression. But the problem is that we don't know exactly what is the upper layer protocol. Of course, we have IPsec in the rule, but it doesn't tell us how to link it. So we have either to analyze the rule and say, oh, it's IPsec, or to put one information in the rule that says the next header is IPsec. But that's complex. So what we, next slide, please. So what we propose to do is to add a stratum header that is something specific that use chic. And here we will put an information like the upper layer protocol is IPsec. So when we do the compression, so next slide, we still sending an IP packet on the internet, say the next header is chic, it arrives to the application. So the application take all the chic part. So first decompress the first element and learn that the upper layer is IPsec. And then we'll do the decompression of the other layers. And so we will have a regular packet. So next slide, please. So this way we can put in IP the fact that is no more chic, it's IPsec. So it's a little bit like in IPsec when you are pointing to IPsec protocol, and then inside IPsec you say what is a real next header. So what we propose to do on the next slide is to make this present all the time, even if there is no bit. I remind you that when you have something in parentheses, maybe there is no bit on the wire, so no impact. Is that before each instance, we add a stratum instance that will help us to carry some information that are needed to manage just chic process. Okay, next slide. So here is an overview in 3D about the same thing. So we have the endpoints in different color that the compression for all the protocol. And before that, in red, we have the chic stratum instance that carries some signaling information for chic. And so an endpoint and a chic stratum endpoint make our instance, make the next slide, make an instance. So it's what we have normally on the next slide. So we have these blocks that are now what we will manipulate in chic. So next slide. So here is what you find in the draft. So there is a mistake here. It should be a chic instance endpoint. You're talking
Laurent, if you excuse me, there is a question on the discussion about what is the difference between an instance and a stratum. So I kind of answered on the chat, but it seems there is this confusion. Maybe we should explain again a little bit what the instance is versus what a stratum is.
So a stratum is the group of two chic instances, one that is a chic stratum instance that is for management, and a chic instance that is here to compress or fragment chic as usual. So stratum is the combination of these two elements.
So but the instance is this quote unquote session between two endpoints, whereas the stratum is more like what a layer would do, like dispatch, understand what's going on, etc., etc. So one is more like a layer, that's the stratum, and the instance is more like A is talking to B. So it's this relation between A and B. Stratum is a location in an architecture. Instance is something active where two people are talking to.
Okay, so we will
Yes,
look to some example after, but stratum is a block that we are manipulating and is composed of SCHC instance and a SCHC stratum instance. So maybe the SCHC stratum instance is empty, but it could be here. So the first thing before going more in details into stratum, so we introduce also something, so the name is not that nice, but we call it discriminator. And it's when you receive a packet, a SCHC packet, you have to find to which stratum instance you have to send the packet. So it's external information.
Laurent, we have a queue.
Sorry? Yeah, Antoine?
We have a queue, yeah. So it's Bob is gone, and then there's,
okay.
He's back. And then there is Antoine.
I just want to say that, in a sense, this is not a new issue. We had this, we were even looking at DTLS, and that inside the DTLS, what compression we'd be having versus the compression outside of DTLS. So this is really not something new to deal with. It's just that now with IPsec and a few others, we now have more, it's becoming more apparent that we needed clarification. That's all I wanted to say. That I was already looking at how I was going to do this before.
So,
Yeah.
So from implementation point of view, it's very easy to do because you have always the same mechanism. You are just pointing to a different set of rules.
Right, exactly. Just want a different set of rules at whatever level you're at. So you're clarifying the nomenclature and the architecture, but this is not something that we're just simply we're doing. Is all I wanted to say.
I had a question regarding the stratum instance and the instances. So in a stratum, you have instances that are like a data layer and the stratum instance, which is sort of management layer. Is the stratum instance common to several instances? Because in the terminology before you say that an instance is point-to-point. So do you have a couple of stratum instance for point-to-point, or you have a shared stratum instance that distributes the management information, whatever the instances that belong to a stratum?
So it's still a point-to-point association. So you can, maybe Pascal, can you go on the next slide? There is a drawing, no, next, two more next.
So maybe if it comes next, I can let you continue.
So this one, for example, I mean, I don't know if it will be clear, but you have, for example, on the right-hand part of the slide, so you have, for example, some SCHC instance that are, for example, electrical meter that are using a non-IP technology to send the information to a concentrator. And this concentrator is sending on IP the SCHC messages. So what the SCHC stratum instance is doing is to add some information to identify who is the sender. And so it's the red part. And when you arrive on the other end on the red part, so you know, using the instance ID that is sent, that you are able to identify which upper layer instance you have.
So you have one, in this case, for instance, you have the concentrator. In fact, in the concentrator case, you have a tree structure, so it's quite easy. But for instance, if you had a concentrator sending to two routes, potentially, you would have one stratum instance with each route and one instance with each route.
Yes, we keep the point-to-point association.
Okay, thank you.
So let's go back to the discriminator. So the discriminator is something that is outside of SCHC and that helps us to identify the SCHC stratum instance we are using. So it can be the IP address, for example, in a 6-law environment. When you receive, you are in a mesh network, and you have to identify who is sending, which rule you are going to use. So you use the source address of the sender to find where to point the information. And if you are in a node that talks with different nodes, then you will have some SCHC instance that will be identified by the IP address. But it can be anything, other things. It can be a TLS, DTLS association. It can be MPLS labels, or anything that helps you to recognize what is the SCHC stratum instance. So, and the funny thing is that in the first RFC, of course, we didn't have the vocabulary, but we talk about the end of the tunnel, and it was a kind of discriminator. So to go back to Bob, Alexandre, okay. No, but it's
Yes, it's just yes. There's just something that, but you said it before. I think here it's written SCHC instance, but it's the SCHC instance endpoint. It's the SCHC endpoint in this graphic, right?
Yes, there is an error
This
in
is
the
the endpoint.
SCHC instance endpoint on all the documents, but I will write it too late to change it. Can you go back to the previous slide, Pascal? So here we have a case, for example, where you have no set of rules that define your SCHC stratum instance. So it's empty. So it means that you have no context on both ends. So you don't care about the SCHC stratum header. It doesn't exist. And you go directly to your SCHC instance. And in that case, we have the compatibility, and we are in the same case as what we got with we had with LP1 architecture. So we have a discriminator, for example, this is a tunnel endpoint, and then we go directly to the SCHC instance endpoint. The other case is, for example, what we say for the IPsec case. So it means that we are sending the SCHC, the upper layer protocol, and we are using a SCHC rule to define it, and we say a SCHC proto, for example, and we have a value. If we look at this this rule, we have only one rule, so no RID is needed. And here we are not sending any residue. This means that here we are sending the information to the other one, or the other one knows by the context that the upper layer is IPsec. So we don't have to send really information for this, or bits for this SCHC stratum header. And the last case, so it's the one with the meters. So as we explained, so here we have a rule that defines, for example, here a SCHC instance identifier that is usually on 10 bits, but we are only sending the last 3 bits as a residue. We have the SCHC proto that so upper layer that we don't send. And here we introduce also a CRC, because, for example, we have eluded the UDP CRC and we want to protect the packet. So we can do it by describing this kind of thing on the SCHC stratum header. Okay, so here are the definitions that I'm not totally convinced, but it's the best we have right now. So SCHC stratum is a fundamental block of the SCHC mechanism that can be stacked at different locations of the network. And it's composed of a SCHC instance and a SCHC stratum instance. A SCHC stratum instance is used to carry some specific information to control the upper SCHC instance in the stratum. This has include, so we say CRC, protocol identifier, an instance identifier. We can imagine also, for example, to send the MTU you are expected for the fragmentation. So all these things are possible. And the magic of SCHC is that we just define a rule to say what we want to send. So we don't have really to specify the format. It's the rule implementer that will do it. And the rule also forms the serialization on the link. And so what we are sending on the link. So we are reusing fully all the SCHC mechanism to do that. And as I said before, when we implemented on OpenSCHC, it was just with a rule manager that point on different set of rules but the rest has not changed. So that's the interest. So here it's, I would say
Laurent,
that the,
Laurent,
How much
you
time?
have 10 more minutes plus a few for questions.
Okay, so I think it's good because here I will say that it's things that are not so well defined right now, and we have to discuss on the mailing list. So now is to say how we can do the management of the SCHC rules. So the goal is, for example, to use CoreConf to manipulate rules and create new rules, or to modify some values inside the rules to do better compression. So what we propose right now is to add a new kind of rule, which can be compression, decompression rules, but we will not call it compression rule, but management rules. And only these rules will be able to manipulate the content of a set of rules. So to add new rules or to add new rules or to change some value inside the rules. That's why we need also the access control draft to say which field can be modified in the rule. And if we go in that direction, can you go back, Pascal? If we go back in this direction, we have to say how we will do the CoreConf mechanism. And to do that, do we use CoAP? So we have to do security. Are we going to use OSCORE, DTLS, or do we allow all of them? So for me, for example, IPv6 can be a very simple IPv6 with 2 linked local addresses, because we are in an instance, so we are point-to-point association, and we can have FE80 column 1, FE80 column 2, and we say that the application has this value and the device has this value, and that's all. And then we put to DP, we create some very simple compression rule for IPv6 to DP and maybe OSCORE, and we can carry management on that, and it's really specific to the set of rules. We have no confusion with other protocol we are compressing. So that's something, but of course it's just ideas. We have to go deeper. And the other things we have to study, and I think it's a little bit more complex for the first one, it's about rule provisioning, how we set up complex rules inside a SCHC environment. So we already discussed that during the interim meetings. So for example, a rule can be the combination of different things. You have the manufacturer that knows the flow is sending. You have the network provider that knows the IP address is giving to the device. And you have the device owner that knows the IP address of the application. So when we want to use SCHC, we have to combine all this information securely to create a rule that can be active. So how we name these rules, how we change these values. So it's something in my point of view, we have to put in the draft. And we have also to look in the document to global action, because I accept to remove it from the OM draft, but I think it's something very important, either for ping or for ANA's flow management that allows to create dynamically rules, for example, to compress TCP or anything that can be viewed as a flow. So there is also a lot of work to do to continue on this document. And that's my last slide. So there was also Alex that put some slide after. I don't know if you want to discuss them.
Well, probably maybe if you can take a couple of questions. There's maybe one slide I'd like to present, but probably take the time for, if you have any questions, and then I can take 2 minutes to present it.
So do we have questions? So Alex, I guess if you can just tell me what slide number you want to jump to.
Yes. Okay. So you can move forward.
Yeah, is it the mic?
Yeah. It's about the. Okay, yeah, that was actually, yes, on naming headers. Okay, well, so yeah, so this is the slide and the next one. So basically, of course, one of the things that we've been doing, and it's not a simple task actually, was really to to make sure that we name things correctly, because some things were a little bit ambiguous in we had different interpretations. We are all agree basically on what they are for, but it's like there are very slight cases around the edges that need to be cleared out. And also because right now we are really writing everything in the architecture, there are things that were never really, we didn't need to write them down, and now when we're writing them down, then we're like, okay, how do we name this correctly? There's one thing that I think we don't really name correct. I mean, we didn't really name it explicitly. So next slide, please. It's actually the SCHC header, right? So it's really like a very obvious thing to say, but okay, well, the formatting is a bit off, but it doesn't matter. But basically, we have in RFC 8724, we are using the term SCHC compressed header and SCHC fragment header. And actually, there are several types of SCHC fragment header. And basically, both of them are like, well, rule ID plus something, like rule ID plus residue, that's the SCHC compressed header, and rule ID plus the DTAG plus something else, that's the SCHC fragment header. And while we were actually rewriting, like writing the architecture draft, it's a little bit cumbersome to every time say like SCHC compressed header or SCHC fragment header. So a suggestion, an idea, and a proposal is to, next slide, please. Next slide, Pascal. Yes, is just to say, well, this is the SCHC header, right? So when we say the SCHC header, it's this thing, right? It's the rule ID plus the thing afterwards, and that's where it can, and it refers to the compressed header, to the fragment header, or when we have the stratum plus something else, like the whole thing, that the bits that go on the wire are the things that we call the SCHC header, right? So, like, if you have any feelings about that strong, or just don't hesitate to say, yeah, well, I don't think that's just, but just I think that this is like, this is going to the architecture, and then when we say SCHC header, it's like, okay, the rule ID plus the bits. So next slide, please. I think that the next slide was, yes, okay, well, and then another thing, and I'm going to stop here with this one, is that at some point it was like, okay, well, how do we actually call the whole thing that we're sending over the wire? Like, it's with the SCHC header and the payload that goes with it, right? Because again, in RFC 8724, we treated the compressed things and the fragmented things differently. So a proposal is to say, well, SCHC packet. So that's one thing. So that's the output bit stream resulting from the application of the compression on the input bit stream. So very generic thing, and this means that it includes the SCHC compressed data and any necessary metadata for compression and decompression of that. And so SCHC packet, and then SCHC fragment. So that's the resulting from the fragmentation, compression and fragmentation. And so when we want to use a common term just to say, hey, whatever gets out of the SCHC machine, like, we don't want to say every time, well, either the SCHC packet or the SCHC fragment, is to invent a new term, well, the STU, so a SCHC transmission unit. And basically it's like, I have a SCHC endpoint, whatever comes out of it, like, this is the SCHC transmission unit, this is the STU. So this is something new, and it's just to say, well, you know, we are we have ways to name, like, whatever comes out of SCHC, it's the STU. It can be compressed, compression, it can be fragmentation, doesn't matter, right? And we know that its header is a SCHC header, no matter what happened there. Like, so again, it's this is all the effort that we're putting in actually naming things correct, naming things in a consistent manner, and that help us express them shortly, right, in a concise manner. So that's for me.
So do we have any reaction on those terms? I mean, does it make sense, Daniel? You're going to like?
Yeah, to me it makes sense. I mean, I think it's quite important to have the right names, and to have a name first, and then the right one is if possible. But the one you proposed to me makes sense, and the answer to questions I had while reading the document. So this is heading in the right direction. Just a feedback.
Yes, guys.
So,
Carlos, yes.
yeah, so I think it makes sense to do this effort. I was wondering if just a very tiny comment, instead of SCHC transmission unit, what about SCHC data unit?
I have no strong feelings about that, right? We were thinking stew, like the soup, because we said that it outputs. Laurent likes always saying it outputs a soup of bits, so we said like it's a stew, like but it can be. I really no strong points on that, and I would just like maybe send an email on the mailing list and we can discuss that. But I think we need to agree on something, and it can be SCHC data unit. I have really no issue with that. And we put that in the next revision of the draft, and from here until the end of the universe, it's going to be called stew or stew or or whatever. Thanks.
We'll check that in Dublin.
Okay, and with this, we'll move to the next topic in our agenda, and that's no, Carles, since you are close to the mic.
And just before Carlos start, can everyone in the
Yeah.
room be sure to log into the application? That's important for the blue sheet, so we can record who is going there and basically get the right size of the room next year. Thank you.
I'm not finding slides for you. I don't remember whether you sent us slides, Carlos. Did you? Oh, yes, that's it. Sorry, I was not finding it.
Okay, thank you. So my name is Carlos Gomez. I'm going to present some of the main updates in the last version of the draft entitled Transmission of SCHC compressed packets over 15.4 networks. My co-author is Anna Minabu. So these main updates have been as a result of trying to align the draft with the SCHC architecture document that has been presented by Rohan, especially by with the latest developments there. So by the way, this is a 6-law working group draft. So the presentation will focus more on those aspects which are most relevant to the SCHC working group. And then a more detailed presentation will be in the 6-law session on Wednesday. So please feel free to attend it. So yeah, in this document, we have the goal that's shown in the slide. So on the left, you can see the, sorry, previous slide. Yeah, thank you. So on the left, we can see the traditional protocol stack based on IPv6 over 15.4 networks, which is enabled by means of 6LoWPAN as the adaptation layer. And what we want to do in the draft is offering an alternative technique for header compression, which in this case would be using SCHC, because we have the expectation that it would be possible to achieve greater performance. Next, please. So we have added a section 3.2 on the SCHC architecture concepts on how these concepts would apply in our case. So first of all, about the SCHC stratum in our draft, which is the SCHC is used to compress IPv6 packets over 15.4 networks. The SCHC stratum is located on top of layer 2 and below layer 3. And one aspect here is that the compressed data of the SCHC stratum may also comprise upper layer packet headers. There are several options here, like SCHC may be used to compress only IP or maybe IP/UDP headers all at once, or IP/UDP co-op all at once, and so on. About the discriminator, in this case, we understand that it would be, actually, it's the first field in the 15.4 frame payload, which would be the 6LoWPAN dispatch tag. So when it's set to SCHC dispatch or SCHC pointer dispatch, then it indicates that what comes next is a SCHC compressed data unit. Next, please. We have also introduced a couple of terms in the draft of our own. So these are single instance networks and multiple instance networks. By the way, there's this box on the top right side of the slide, which shows some terminology. On the left there, you can see the current terms which are being used in both drafts, this one and the architecture draft, and on the right is the new terms that are aligned with what Laurent has presented, and also the ones which are used here. So, okay, back to the definitions. Single instance networks are those networks where all the nodes have a single SCHC instance for compression and decompression, and therefore each node has a single set of rules because there's only one SCHC instance. And in that case, the SCHC stratum header, which is what tells what instance needs to be used for compression decompression, is less relevant here because there is only one possible SCHC instance, and it means that it can be fully compressed. And actually in the draft, we require it to be, so we say it must be fully compressed. So it will represent 0 bits sent over the air. Then also all network nodes have a single SCHC stratum header and a single set of rules for SCHC stratum header compression decompression, which is like actually empty or equivalent to compressing a single implicit rule for SCHC stratum header compression decompression. Next, please. Yeah, Alex?
Yeah, can you go back on the previous slide? You just yeah, just so thank you. I'm just trying to no, it was the one after. So yes, so here you say all network nodes have a single SCHC instance. So I get the feeling that here you're using it in the sense of that you can have one SCHC instance spanning over, like it's more than 2 SCHC endpoints, right?
Well, this is basically opposed to having different possible instances. So the idea is each node has only one set of rules.
Yes.
Compress and decompress. So.
Yeah. I mean, it makes perfect sense, right? But it just, I mean, it echoes with the discussion we had before with like is a SCHC instance limited to 2 SCHC endpoints, or is it like it can be more? So I get the impression that here it's like you can have like 50 nodes, and they all have the same compression decompression rules, and in that sense you say, well, it's like there's the same SCHC instance there on that.
Yeah. So that's a
okay.
point. Yeah, I guess we may align and see whether actually the SCHC architecture draft will define these details or whether we need to include them here. But yeah, it makes sense to consider this. Yeah.
I mean, personally, I like it. It makes sense to me the way you write it like this, but it's just, yeah, we need to make sure that the architecture is needs to reflect that. But thank you.
Yeah, thank you.
I think Daniel wants to.
Daniel, you.
Okay, so that's just a clarification question. Suppose you have an IPv6 packet and you have 2 different compressors, one that compress one header extension and another compressor that compress another one. So when you receive the incoming packet, I mean, you will have in your extensions, and so you will have 2 sub-SCHC packets in it. Does the stratum will reference to the packet the packet that is being compressed, so the header being compressed, or the instance of the compressor?
Yeah, so I understand that the SCHC stratum header indicates the instance that needs to be used to decompress the packet.
Okay, right. Because one thing is that these are not protected. So, if I play with the 2, just changing the number, I mean, it might have some impact.
Yeah, thank you. Okay, so Bob?
The point that more general, broader question, and that is, I believe that 6-low header was done prior to 15.4 adding ether type. Originally, 15.4 did not have ether type at all, and 6-low had to play games and how it worked. Later, as a result of my work in 15.9, 15.4 was able to add ether type. So now there is ether type over 15.4. Thus comes the question, now when we're talking about having SCHC as an ether type, how does this work where you're sitting above the 6 low discriminator? How does this work, and how might it work differently if we had SCHC as the ether type underneath the 6 low? Does this, no, would we have potentially a broader architecture, because then we can deal with other things over 15.4? I raised at this point, obviously I'm just now looking at this, and also that my 15.4 work is over 10 years ago. So
Yeah, so far we had basically used the 6-LoWPAN dispatch field to then determine what is being carried in the frame 15.4 frame payload. But that's an important point. We hadn't looked at the ether type. So yeah, we also need to consider this along with the, well, perhaps in the context of the discriminator to be used here. Yeah. Okay, so yeah, continuing, multiple instance networks would be those networks that have at least some nodes with more than one SCHC instance for compression decompression. Therefore, those nodes will have more than one set of rules, because there is one set of rules for each instance. And in this case, the SCHC stratum header cannot generally be fully compressed. We will need the SCHC stratum header to tell, okay, which of those instances is the one that needs to be used to compress or decompress data unit. And this means that generally it will be more than 0 bits sent over the air representing the SCHC stratum header in compressed form, although there's some exception I'll mention later. And also all network nodes will have a single SCHC stratum header, a single set of rules for SCHC stratum header compression decompression. And in this case, that set of rules may comprise one or maybe several rules for SCHC stratum header CD. Next, please. Okay, so in this 6-low draft, we have one of the main problems is how can we deliver a SCHC compress packet over a 15.4 multi-hop topology. So for that, we have currently 3 route over modes, and we have also mesh under, and now we also have to consider single instance and multiple instance networks. So in the interest of time, I will just focus on a couple of examples here, and again, all the or more details will be provided in the 6-low session on Wednesday. So what we can see here on the slide is one of the route over modes. It's called straightforward route over, and it's based on having the intermediate nodes, the 6LRs, storing all the rules which are in use in the network. So in this case, for example, let's say that host A wants to transmit the packet to host B. It would use rule ID 1 to compress the packet header, and then it would send the packet to the next hop, which is the upstream 6LR. Then this one receives the packet, and here, because this is single instance networks, there is only one rule ID 1, and the 6LR can perfectly decompress the packet and perform its routing decision, send the packet, compressed again to the next hop, and so on. So the conclusion here is that because this is single instance network, then the SCHC stratum header can be fully compressed down to 0 bits. Next, please. But then what happens in multiple instance networks? Well, we have another example here with 2 instances, I1 and I2, and some of them are highlighted in red. So let's imagine that host A receives the SCHC compress packet with rule ID 2. Host A would be wondering, okay, which one of the 2 possible options we need to use to decompress this packet? So we need, in this case, a not fully compressed SCHC stratum header to tell which one of the rules is that the one in instance 1 or the one in instance 2 that needs to be used to decompress the packet. So actually this kind of conclusion applies also in the next the other techniques that we use for route over and even for mesh under, with some exception that I'll mention later. So if we can jump to slide number 13, please. sorry, number 13. So yeah, this one, thank you. So, okay, here there's some exception in mesh under multiple instance networks, because in some cases here, a fully compressed SCHC stratum header may actually be used. So, for example, again, we have host A. Let's assume that it receives SCHC compressed packet with rule ID 2. So there are two possible options, two possible rules here. One, the one in instance 1, the one in instance 2. So here, this is a special case because, as you can see in the rules on the right side of the slide, one will have the source of node C. The other one, the source will be node D. So if host A can tell who is the source of the packet, then based on that, it can determine which is the rule or the instance that has to be used for decompression in this case. And this is possible in this particular case because this is mesh under. And then, because it's mesh under, we have a mesh header, which includes who is the origin of the packet and who is the final destination. But otherwise, if maybe there is like from the same two endpoints to instances and the same rule ID, then there will be ambiguity and it will not be possible. But at least in this case, it is possible, even if it's multiple instance networks, to fully compress the SCHC stratum header down to 0 bits. Mohan?
Yes, something I don't understand is the notion of discriminator here, because for me that fits well because you have addresses and you say, so I go to this instance with using these addresses.
So yeah, I noticed that when you presented the discriminator, we had like different views, and perhaps I might need to update my own. Somewhat I understood the discriminator as some field telling, okay, what comes next is a SCHC header or a SCHC stratum header. So it is rather in this interpretation about at which kind of layer, more specifically, which stratum we have there, or that there is a SCHC stratum present there, rather than the parameters that will allow to determine exactly which instance would be used. Because actually, I understood that which instance is used to decompress the packet is part of the SCHC stratum header. So I don't know. This is my view, but maybe it needs to be modified.
No, but we have to discuss because that's very an interesting point to fix the architecture. For me, it's you have two ways to. So the first one is that the discriminator points on the SCHC stratum instance, and then inside the instance you may have another instance ID that points to the right instance. But this second one is not mandatory.
Okay. Okay. So yeah, I guess we may need to double check our understanding of the architecture. Yeah, thank you. Okay, so next, please.
Carlos, just for the time, you can have 3 minutes to wrap it up.
Okay, because there was a question that Laurent was supposed to relay, I think, but we can have it in the end from Aman Van. So let's finish your presentation and we'll see if we have time for questions. Please try to give us a minute for the question.
Yeah, so next, please. Okay, so basically we have updated all the frame formats in the draft. So the SCHC packet, which is the packet with the SCHC compressed header, now is preceded by a SCHC stratum header, which again, when it's in single instance networks, it will be fully compressed down to 0 bits over the air. In multiple instance networks, it will generally be not fully compressed, with the exception I mentioned before. And in this case, what we recommend in the draft is that the rule ID for that would be a size between 1 and 8 bits. So the SCHC stratum header in compressed form would be something like a rule ID and a compression residue. Next, please. And the next steps, we have to define which is the SCHC stratum header format. And we also have to define something for the transition protocol stack, which is an approach kind of intermediate between the original 6LoWPAN based protocol stack and a SCHC based protocol stack. So here 6LoWPAN would be used to compress the IPv6 header, but SCHC would be used to compress upper layer protocols. And in this case, we need to decide, for example, whether a single SCHC stratum is enough for compressing UDP and CoAP altogether, or whether we may need one particular stratum for each protocol. So this is things to be sorted out in next versions. So yeah, that's it. So maybe comments or questions?
So we
Yeah,
have.
so sorry. I'm then at these questions about why are we compressing the packets but not fragmenting them using SCHC? And there are a number of reasons. And, I see that the thread is already providing a number of those answers. But the design of the fragments in SCHC is very different from the design of the fragments in 6LoW. And there are things that we are doing at 6LoW, like forwarding fragments that you cannot do. So maybe in the case of Messenger or in the case of Ethanol, you could be using the SCHC fragmentation because the forwarding is not involved in that. Also, there is the transition stack, which could not be using it because it's compressing above 6LoW. That's what I answered. So but basically, if you look at the design of the two fragmentation, they are quite different because one was thinking mesh and the other was thinking protocol.
Yeah, so in addition to one of the things you mentioned, one reason why we would still keep the 6LoW pan fragmentation or 6LoW fragmentation, including your latest draft RFC on that, is also to somehow allow reusing existing implementations, existing code, as another reason why we might want to keep that. However, yeah, there are also, especially considering your RFC, Pascal, about 6LoW fragments with recovery and so on. I had the impression that maybe it's not so different now how there is SCHC fragmentation, at least compared with the original 6LoW pan fragmentation, where there was no retries for fragments and so on.
Yes, so we have passed the time and would like Marco to jump to the mic if Marco, you're here. Thank you, Carlos. Thank you so much.
Hi, can you hear me?
Yes.
Good. Okay. Hi, everyone. This is Marco Tiloca. This is an update on a working group document on using SCHC for compressing CoAP headers. Next slide, please. Right, as a recap, this was adopted as a working group document at the end of last year, right after we pushed version 0. Then we did a meet in March in Brisbane. So we are in version 2 now. I'll try to present a consolidated update. But the goal of the document, as was mentioned by the chosen in the introduction, is to obsolete ATA 24. So, of course, the scope is the same, describing how SCHC is used to compress CoAP headers. But in this piece document, we take the opportunity to provide a number of clarifications, especially on different already existing and new CoAP options to be handled by SCHC, on some particular corner case fields like the payload marker, and provide also tons of examples to clarify how SCHC is used with proxies. And by no means we intend to change the core rationale and philosophy of how SCHC is used with CoAP. It's just clarifications and additions. Next slide, please. So again, jumping from version 0 to version 2 that we have now, I'll go through the updates here. And first of all, we took care of one of the errata that were filed, I think last year, that got approved but held for document update. So this was about time. Right now, the text in version 2 is enforcing what was expected in addressing this errata. There was an example of a SCHC compression rule that was using =1 in DMO, and the real intention was to stress instead that the goal was to target the first element of the path targeted by the CoAP message. So what you see on the right is now the resolution of the erratum as it was intended. While working on that, I had a thought if this can even be simpler than this, and if TV can simply be element of the path or just any, or any canonical wildcard value if we had any. I don't know. Because it should be clear already from the FP with value 1 that we are indeed considering the first element. And yes, this is about the path as the field descriptor name says. So any thought, anyone on this?
I don't understand why you say simpler, because you just have one element as a TV. So
well, you can have multiple elements because the option is repeatable. I'm saying TV is redundant here compared to what field and FP are telling you already. So maybe just saying any in TV, any value present there is just to be omitted and not sent.
what you can do is, for example, in the document, it's possible to have two elements as a TV. So you can have /A/B, for example, and it's viewed as only one in the compression. But normally you separate them. What is not very well done, I will say, that you need to have the right number of options of element in your path to match the rule. And if there is some tricks, but using a variable or something that say or a known to limit the size, but it's not very, very nice.
Right.
But if you have ideas to make something clever, it's fine.
Yeah, any value is supposed to be suppressed here, basically. That's why I also thought of a wildcard, but I don't know if there's any official wildcard defined for SCHC.
But if you have ignore, it's like a wildcard.
Sure, that's another way to take it then.
So the other thing is that you can use MSB on the path. So for example, if you have always the same thing at the beginning, the same letters, then you can cut this letter and just send the remaining part.
Okay, that's a bit of a different rule, but yeah, sure. Daniel?
So one thing that might help you, but I'm not sure, is that in IPsec we have any and opaque for matching traffic selectors. I'm not sure I would take that path.
Yeah, if it existed at all, my understanding here would be something like any, but yeah, if it's not admitted by 8724 in the first place, I don't want to introduce something that can create confusion either. Okay, minor thing anyway. We are aligned with the intended erratum resolution. Okay, on this slide, we also had a number of clarifications related to the compression of co-op options in general, and the text describing how they are represented in the field descriptor of a SCHC rule. This is not really changing anything on the process for compressing options. Is just awfully clear text. And in particular, the delta property of a co-op option is not really, the type property of a co-op option is not really taken into account anyway, so it could be easily stripped out from the description for the sake of easy understanding. And FID is not necessarily the option number like the text was saying. It's in general an unambiguous identifier of the option, and practically, as you see in all the examples, it is the option name. And on the FL, the text was saying, like in 8724, but it's actually supposed to indicate the option length. That then, of course, if you send the option in the compression residue, you transmit encoded like 8724 specifies. Next slide, please. And yeah, again, on the options, on the criteria for their high-level compression, the delta and the length that are part of the official COP definition of an option do not play a direct role here. Delta does not, because you still have the sorted field descriptors anyway in the rule. Length plays no direct role either, because what matters is FL, and of course, depending on the operator, you may have to encode it on the wire together with the residue. So just summarizing here the practical ways that, as usual, you can use to compress the options. And D and L, again, directly don't play any particular role. And again, no change in the practical intended way to compress the options. Next slide, please. Some actual change instead. These were already defined options also in terms of shift compression, among others in section 5.5. I'm talking about ETAG and if match. And before version 2, they were defined only to be transmitted as is, with no compression. But actually, even before adoption, we had another option in a similar situation, request tag. And I think Anna noted and proposed that we could also admit for that option to be processed by a rule with MO match mapping and CDA mapping sent. And I noted, oh, well, the same actually can be done here for these two ETAG and if match options. So it's still possible to send them as is, of course, but if the setup of possibly pre-known values allow, you can also go for match mapping and mapping sent. Any objection on this addition? Heard none. And yeah, in the same spirit of double checking what best can be done for options, I noticed that if none match was also described as to be always sent as is, but actually this option is defined in the first place in co-op to be only empty if used at all, zero length value. So practically, it's about treating it with MO equal and CDA not sent, which is consistent with what we do for another co-op option that can be only empty with zero length, the ADOC option. Hopefully, this is non-controversial too. Okay, next slide, please. Yeah, I also mentioned two new recent options that are defined in a core working group document. They are proxy CRI and proxy scheme number. They are basically the more compact equivalent to two long existing options, proxy URI and proxy scheme. They have the same meaning, just in a compact way. And from a SCHC point of view, they are really supposed to be handled and compressed according to the same logic. Next slide, please. Mostly thanks to Laurent, actually, we finally have a complete first version of the Young Data model, not only floating, but actually included in the appendix A of the document and also available as a separate file on the GitHub repo. For the sake of readability, the elements are sorted into sets, field ID and function length. And even though I got validation errors at submission, if you check now in the data tracker, it actually successfully passes validation with pYoung. And of course, we keep this up to date if we made any change or add more option or fields. Next slide, please. Yeah, to conclude with IANA, this one, yes. Something was quite simple and expected to do anyway, looking at other SCHC-related documents, the requested registrations in IETF XML and YAM module names. And then we thought of IANA to address an issue that was brought up also in previous meetings. We ended up, after some discussion with Laurent, mostly in Paris, to propose a new IANA registry. And this is the issue. We expect in the future, of course, to have people defining new co-op options or co-op headers in general, or updating those, and that's fine. After thinking a bit, it's a bit too much to expect from people that at that point in time, they also define how the SCHC compression should work for those options and fields. So the two things should be really decoupling. One is defining or updating co-op header fields. One is, if there is any interest or need, defining the SCHC compression for those. That's on one hand, but on the other hand, I suppose we don't want to come back over and over every 5-10 years, whatever, with a new BIS document realigning the current state of the art of SCHC and the co-op world. So a possible way to address this is basically setting up an IANA registry as a sort of catalog of existing co-op header fields and pointers to specifications that define how those are handled with SCHC in any known way. Next slide, please. Yeah, there's more details on the draft, of course, but this is the gist of the registry, and it's really simple. And the catalog with 3 columns only. Field is supposed to be the unique field identifier for the co-op header field, and it's supposed to be used really as the value of the field column in a descriptor of a SCHC compression rule, and it's supposed to have a companion entry in the Young data model. Description is supposed to give a simple description of that and pointers to specification where the co-op header is defined. For example, the co-op RFC, if it's one of the original ones. While reference instead is supposed to have a set of references to documents that define a way that has been proposed to compress that co-op header field with SCHC. And we are, of course, pre-populating this registry with everything we know about this topic today based on a table that we have in a separate section. And I think specification required could be a good fit as a policy where the specification in question is the one describing how SCHC is used for that co-op header field. And we have, of course, guidelines for the expert in a dedicated section. Just a summary of next steps. I think it's better to clarify yet another thing tacitly assumed so far on the compression of the TKL field, but no change in the behavior. We need security considerations on the Young data model and a few advanced things I'd like to think more, including possible better positioning of some text in different documents that this was also raised before. And a final administrative point, the sources of this draft now are hosted in my personal GitHub. It started this way. It's fine to me. I believe it's more appropriate to have those in the LP1 GitHub organization, I think, but I don't have the privileges to create a repo there. So if anyone, the chairs can create it, I can migrate the sources there. And that's all from my side. Thank you very much.
Thank you, Marco. We'll take that offline and we create that repo. We are 10 minutes behind, so I think the next is Anna about network susceptible to disruptions. Anna, please start. And yes, if you can be quick, that's nice.
Yeah, thank you, Pascal. So I will present the update of the adoption. And the first title was SCHC for zero energy devices. And after some discussion in the mailing list, we see that the disruptions can not only be about energy harvesting, but also about disruption in connection or the latency. So we try to open the scope and change the title, but not only. Next slide, please. So the context will be, again, different topologies, but with different devices capabilities. And the most important will be to have this scope with the energy, with preserved battery, and the energy harvesting as was proposed first. And the second part will be, as we have discussed with, I don't remember his name, Rodrigo, yes. With Rodrigo, we discussed about the satellite networks with Leo, that the disruption of connection is done because the satellite passed. So at the end, the result is the same. We lost the connection once because it's energy, on the other side is because the satellite is gone. So the use case we can present in this document can show these two possibilities, and also the LP1 for the preserved battery. Next slide, please. So SCHC will help these connections with to simplify the operation in saving energy, with longer delays for transmission timers, lower reliability, and also because
Anna,
we are doing, yes?
can you speak a little bit louder or closer to your mic? Because
Yeah, it's better there?
that's better, yeah.
Okay. And then also because SCHC brings the overhead reduction with header compression and fragmentation, and we can reduce the padding or eliminate it. And also, SCHC will give us the opportunity to tolerate the delay and the long latency. Next slide. So the first adoption is this draft is informational. We changed the title, and the objective now is this. We have three use cases: the zero energy, the disruption connection with LEO satellites, and the low power for LP1. So next slide. So if you agree to adopt this work, the deadline is today, as Alex said. We can vote if you want, because we only received 2+1 at the mailing list, I think. So that's all.
Thank you. Thank you very much, Anna. So, okay, so Pascal has started a show of hands. So, what, of course, the point is that the work initially started as the zero energy devices work, where it is specifically based on a document from the 2GPP, and there were a lot of architectural discussions and all that. So it is a very, very like so there's a clear application path for this document. And then of course it was like basically adopted because we had like a show of hands. Everybody voted for that. There was mailing confirmation on the mailing list, and all of that was confirmed. And now the 2+1s were basically when we said, okay, probably we need to reframe it because it's a little bit larger than just this 3GPP document, right? So I mean, the way I see it, it's like we have all the +1s from before. We didn't get like no one said -1, right? So show of hands. I think maybe we can leave it.
We've got 6 positive, no negative. I guess we're done for today. So we've got 6 more positives, and like I said, no negative. So let's
Yes.
confirm that the draft is adopted. Please publish a 0 as soon as you can, which is
Okay.
probably today. But
Yeah, I will
okay,
do that.
thank you, Anna.
Yes.
Thank you.
And
Thank you, Anna.
let's move straight to the next, which is the SCHC implementation. Javier, if you're here. Oh, Daniel had a question. I see. Are you still? No. Okay. Please remove yourself. I forgot to do it this time.
Hello, do you hear me?
Yes.
Yes.
Do you hear me well? I'll try to put my video. Perfect. So, hello everyone. I'm Javier Fernandez. I've met maybe a couple of you before. I'm an IoT R&D engineer in IMT Atlantique, and we're working right now in Lab SCHC, which is a joint laboratory between IMT Atlantique and Actility. So, next slide, please. Opa. So overall, we have inherited SCHC implementation from a company called Aclio. And this was a company that further developed SCHC, actually made it possible to have SCHC in real life. And this was later acquired, sorry, previous slide. This was later acquired by Actility recently, this year. So Actility had control over IP Core, which is a SCHC gateway. It's a decompressor, let's say, acts as a gateway between the traditional internet and SCHC. Let's call it. I'm not sure if calling it already Stratum. She can't. Yeah. So what we have decided to do is have a joint laboratory where we can open source the SDK, the embedded application, and have it communicate, have it interoperable with OpenSCHC and IP Core as well. so that we can basically accelerate the adoption of SCHC. So where can you find it? You can go to our website. It's lab-chic.fr. And I've put a little QR code. If you're curious, you can just scan it from your phone or just go to the website. There we have 3 large buttons. The first one will take you to the repository. Second one is resources. And third one, you can contact us. You can send us an email. So in the resources button, next slide, please, you will find some resources. So first of all, we have the GitLab repository. Here you will find directly the code. I've also tried to put a comprehensive documentation. So I'm still in, this is a work in progress, but the basics parts are already there. And next we have some documentation links to the business, let's say enterprise SCHC gateway, which is IP core, and let's say the open source, very academic implementation of SCHC. So next slide, please. Actually, we have a couple of repositories for this. We have not one, but 2. So the first one, actually, it's only the SCHC implementation. So here it's called full SDK. So we implemented the full SCHC standard. And this is the repository where the compression and fragmentation functionalities live. There are some additional bells and whistles. There's a DTLS implementation, which is actually super cool, which anyway, it hasn't been standardized. And there's a rule implementation called templates. So this basically translates into the real world where we have actual physical devices that share a common SCHC rule set. However, they have different properties, like say their IP address or so. And there's a synchronization functionality, which is also being developed. Next slide, please. The second repository, which is the delivery package, integrates the full SDK repository, so as a submodule. So it has the SCHC implementation standalone, but it also integrates a couple of more libraries or submodules. So first of all, we have some layer 2 abstraction layers, implementation, sorry. So right now we're just focusing on LoRaWAN, but there's a Sigfox and NB-IoT library. For LoRaWAN, we're using LBM mainly. LoRaMAC is going to be, it's going to reach its end of life soon, if not already, I think. There's a platforms also abstraction layer. So right now we support a couple of boards. So I have some with me. I'm not sure if you can see them. So it's mainly ST boards and also a couple of shields. So SX 1272 and 1276. I had the Nordic somewhere here. Okay, I'll skip it for now, but it's meant to be used with NB-IoT technology. Then there are some libs, some additional libraries that might be used by the application layer. There's an FreeRTOS implementation as well. And there are many examples. Actually, the primary ones are AT modem and the bare metal. So the AT modem, it's like a simplification. We can just use it from a Python, very simple Python application that sends serial commands. And you can try it out like this. There are also some bare metal applications. And yeah, those are the 2 repos. In the docs, I have some getting started guides. I explain also some concepts that are employed within the SDK. And there's also the full reference manual with all the documentation for the public APIs. So next slide, please. So additionally, we are using some CMake to build the applications. We are flashing the device and debugging through OpenOCD. Of course, to build the applications for the embedded devices, we need the toolchain. We're also integrating the Semtech LoRa stack source. And for the memory footprint of the library, we can use FPV-GCC. So here's an example output. The library itself, it's modular. Actually, that's a very cool advantage. So depending on which modules are activated, you might get a different result. Obviously, depending also on your application, specific application. But yeah, here are some data. So over, or more or less, it's like 26 kilobytes, actually quite heavy if you have like a very complete application. But I've managed to fit it in an L0 ARM device, so it's actually, it fits perfectly well, so it's okay. Next slide, please. So how can you participate? Well, I'll just invite all of you to go to the website, just explore a bit, play around with it, clone the repo, try it out. Contact us, please send us your questions. And if you want to see a live demo, I'm open for a call. And yeah, as I said, so this is a work in progress still. We have inherited the code, but now we're making it accessible to everyone. So I hope it's interesting enough, and hope to talk to you soon about it.
That's fantastic, Javier. I hope you look at the drafts that we have and come out, because since you have an implementation in your hand, you can tell us, hey, you're doing something that fits in our implementation, or that's very hard to implement or something. Thank you so much for this presentation. It's huge for this working group to have this implementation.
Yes, just one point, because can you go back just a little, like 2-3 slides behind, because we asked Javier to yes, here with the modules, just for a second, because I see that, like, I just wanted to ask to say 1 minute here, something that's really important. So as you see, there are a lot of modules, and some of them were like proprietary work. Now everything is open source, MIT license, right, from the go. Not everything is fully documented, but we're going to do that with the time. And of course, we'll be adding drafts just to explain, how things are done. Expecting for that to be adopted by the working group, but just, that this code that is there and that's industrial grade work, developed, with no dynamic allocations and all that. I mean, it's writing embedded software that doesn't break. It's very difficult, and you have this kind of code. And there is one thing, like the certification part. For example, this is what you need to get the SCHC certified over LoRaWAN. So you have actually a certification body today that you can go and you can certify your SCHC stack with it, and you have it here. You have interesting work on DTLS, and you also have a very easy way to port the whole thing to a new platform. So it's the L2 abstraction layer that Javier was talking about, and it's basically like 4 functions. It's a C file, and you have send, receive, and set timer. I think these are like the 3 functions that you need, and you can port it to any environment, that any new technology. Like you can port it to satellite, you can port it to ISON, you can port it to whatever you want with these 3 functions. So it's really a technological miracle. Miracle, no, sorry. It's really a bijou.
Technological marvel.
Yeah, a marvel, technological marvel that you have here, and of course, as an industrial product, it's not as flexible as a Python script, right? We will really be very happy that people contribute, and that this opportunity is here, and I think it's really big. So thank you, Javier, for taking care that it all continues, and for the presentation.
Thank you, Javier. We're past the time, so you have a final last word before I bring in the next slide.
On my side, no, it's okay. Thanks.
Okay, Javier, thank you so much. I mean, that's huge for a working group like here to have a full implementation like this one. And Mariam, I guess that's.
Okay. So, hello everyone, and welcome to this. Thank you for joining this session. Today we are going to talk about the ESP header compression profile, and so this document defines the ESP header compression profile or EHCP for compression and decompression of IPsec encapsulation security payload, known as ESP packets using cheek. And the motivation here is to apply cheek on different ESP levels, so we can avoid sending information which are currently shared on the end. And this is a joint work with the IPsec working group in collaboration with IPsec experts.
Mariam, would you like to change the slides yourself, or do you want me to change them for you? I don't see you, but I thought you have your phone with you, so you can decide. I can move the slides, or you just do it.
Yeah, if you could change it, it would be better. Thank you.
Okay, I will change that.
Thank you. So this is the ESP packet structure, just to know. The first part is the security parameters index and the sequence number, which covers the integrity, and the rest of the fields, the payload data, padding, and the pad length and next header actually cover the confidentiality. So here we can see that the security is ensured on the data in detail, including the headers. Next slide, please. Yes, so here we can see the architecture that we provided, the flow diagram, that we can see here the multi-level compression to ensure the security, the side efficiency through the transmission. And just to note that here on top of the diagram, you can see the ESP header compression context is defined by the security association and the additional parameters. We have three main levels of compression. One is the inner IP compression. The second is clear text ESP compression. And the last one is encrypted ESP compression, which we will discuss in the next slides. Next slide, please. So the first level is...
I think we can start calling them stratums, strata actually. What you call levels, that's what our stratas are for.
So the first level happens directly on the inner IP packet, which compresses fields such as UDP ports and checksums. And in case no compression of the inner packet is possible, the resulting cheek packet contains the uncompressed IP packet as well. The next slide, please. So the next level, the clear text ESP compression, or CTEC, compresses the fields of the ESP payload right before being encrypted, as can be seen on the second level. And here we can see that, so the IIP, the C here represents the compression, so we can see that the IIP is compressed, and the ESP trailer, known as the padding length, and the next header are compressed in this level. And the next slide, please. And the last level compresses ESP fields that remain after encryption. Typically involves fields such as the security parameter index, SPI, and the sequence number, known as SN. The next slide, please. So here in this table, you can see the check parameterization for ESP. You can see the EHC context, their possible values, which come from those references in front of it, from those RFCs. And just to let you know that the TS, the context which includes TS before it shows the traffic selector, which is included defined by SA. So you can find variables inside it, which are stored there. And one more thing that I should add here is that the IP address starts and end in front of the TS shows the starting and ending point of the range of the IP address, so we can define the range of the IP address to reduce the overhead here and increase the efficiency. Next slide, please.
Mariam, you have Laurent in the queue.
Yes, just a question about IPv4. It's just a field, or it's something that can be compressed as anything, or it's so there is some difference between IPv4 and IPv6, or you can
It's only the address.
okay, and you can manage it the same way, or it's
Yes,
different?
yes.
Okay.
Yeah. Actually, the examples are included at the end of the draft in the illustrative example part. You can see them more details. So to save more time, we didn't include it here. So the next slide, please. So here is the new cheek compression decompression action that is defined in this draft. So you can see the actions are lower checksum padding and flow label. And we define these CDAs and want to check this is the proper way to use check. And so the lower action indicates that the value is sent in the packet, but not at the expected place. In our case, we have IP in IP. And it means that the compressed field of the inner packet is read from the outer packet. So it can be retrieved from that. The checksum indicates checksum needs to be computed following the specific rules, and the padding indicates padding bits for ESP are generated in a certain way. And the last, which is the flow label, generates a completely new flow label. The receiving generates a new flow label.
Okay, there is a question from Anna. So.
Yeah, thank you, Laura. I have two questions. The first is about what are you using three levels, three stratums, and not only two. And the second question is about the padding.
Can you repeat your question? Your voice, I think it's a little bit low.
Yes. First, I want to know why are you using three levels to do compression and not only two?
So yes, actually inside ESP we have three levels. The first level is the IP inner header, which is the plain IP, actually the simple IP packet that we have. So in this level we can compress the IP header itself. The next level is where the ESP encapsulation comes into account, that we can compress the ESP header in the actually encapsulation level before we go to the encryption, and the last level is for the encryption phase. So in these three levels, we can ensure that we have compression. Not only we have compression and efficiency, but also we can ensure we have the security involved by using ESP as well. I hope I could answer your question.
Okay. Not exactly, but we can discuss it later. And my second question is about why do you need to compute the padding? Because normally we are eliminating the padding.
Could you raise your voice? I'm sorry, I couldn't hear it.
Yes. Why do you need to compute the padding?
So the question, the padding, yeah.
Padding? Okay. So actually, because the padding might be different for ESP, so since it is actually not a specific value to be set, and it will be determined at the endpoint. So this is why we have competing padding to be able to change it in different scenarios. Yeah. So next slide, please. Yes, so this is the one example that we included, and so you can see the IPv6 inside the IPv6 example. The first, we can see the ESP headers, which comes before the IPv6 header, and then we can see the TCP ports and the sequence number and the information from that. And the last part is the ESP trailer that you can see the paddings and the pad lengths. And so this is an example that you can see how it looks like if we have IPv6 inside IPv6 here. And the next slide, please. So in the next steps, we are going to complete some sections of the document which still need some work, like the padding, that we want to see that if we are going to reduce the size of it into bits from bytes, or remove some of the, like the first layer padding, or the rest of them to make it more efficient. And the second thing is that the implementation is in progress to justify our work and this draft. However, meanwhile, we are more happy to receive any comments from CHC experts to read the draft and see that if this draft aligns with the way CHC is defined. Thank you so much.
Thank you so much, Mariam. I guess we won't have time for questions. I mean, but you guys can go to IPsec as well to discuss this. This is the official end time for our meeting. We thank you all so much for attending, and Mariam, thanks very, very much, and Daniel, for coming and presenting that to us. That's very, very interesting. And in my view, quite consistent with the work we are doing in the architecture, if you call things strata as opposed to levels. And yes, Alex, do you have, or Eric?
Yes, just this. Thank you, Mariam. And it's a really important work that you're presenting, and it comes at a perfect time as well to able to to include it in the definition of the architecture as well. So really perfect time. Thank you very much, and thank you all for being here.
And the meeting is adjourned.
Thanks, Laurent.
Thank you all.
Yes, thank you, Laurent. Thank you, Eric, for.
Bye.
And thank you, everyone. See you.
So, bye-bye. I hope we meet in person next time.
Yes. Have a Guinness.